Let us start the lecture number 3 of this module, and this will be the last lecture of AC DC load flow, but not of this module, because in this module I will be also discussing about the transient and the transient of HVDC as well as the AC system together. That will be done in the lecture number 4. In the lecture number 2 I discussed the two methods. One method was the sequential AC DC load flow and second was the extended variable method. In that we were calculating the various elements of this Jacobian. You can see this is the extended variable method, because we are extending the variables of the DC variables here, the x DC, and we are having the corresponding here the column and the row, and here the three equations R1, R2 and R3, those are corresponding to the three basic HVDC equations. So, also we saw this x DC is having the total x DC is the 7 variables, and out of that we have to specify the 4 variables, and that will decide your control mode, and 3 variables we are going to determine through this extended variable method, or whatever you can say, the load flow method. The elements corresponding here, the various elements, the A, C, D and E. A is corresponding to, you can see this is the PT, is your power at the terminal, rectifier terminal and the inverter terminal. So, it is a 2 variable here, this is a vector is represented corresponding to the derivative of your x DC. So, this A is your 2 by 3 matrix, this is also your 2 by 3 matrix, because this is corresponding to your reactive power at the rectifier as well as the inverter. So, 2 rows and here the 3 variables, so 3 columns. So, it is 2 by 3, here the 3 equations are there. So, this will be 0, the D will be your 3 by 2, because this is a corresponding to the voltage terminal. Again we are having the 2 terminal we are talking, then it is rectifier and inverter. So, 3 by 2, and this is your 3 cross 3 matrix. And in last turn we were calculating and we found that this matrix, we decided to calculate this your EIJ, means we saw for one example, that is your control mode A, where we are having the specified variables, your alpha R, that is a rectifier delay, here the extinction angle of inverter, and the VDI, the inverter voltage, and the power at the inverter end. So, these are the specified, then the remaining 3 variable that should be calculated, it is your AR, that is a rectifier tap changer position, here inverter tap changer here, tappings basically, and the VDR rectifier DC voltage. So, 3 variables we have to solve, and since we are having the 3 equations here R1, R2 and R3, then we have to write the elements here. So, here the if it is R1 you are taking here, in that one R1 is this, then this should be differentiated by here this, and we can see it is 0, because this here is independent of AR. This here it should be differentiated by AI, then this also is independent, but if you are here differentiating with the VDR, you will find here this value there. So, -1 is appearing. Similarly, if we will come here, what I have changed, I have done here K1 and K2, because here it is no doubt that K1 is some 3/2 term and by pi is appearing plus into K. So, that whole term here it is written as a K1, because I do not want to write the big mathematics. So, here K1 we can say it is nothing but K multiplied by your 3/2 upon pi. Similarly, here K2 it is nothing but your 3 upon pi. So, in terms of that, if you are differentiating this equation here with respect to AR, here you can say it is independent, no, it is a dependent here. So, this will be 0, partial differentiation of the R2. Here if you are differentiating, this will go off, here K1 VTR cos alpha is appearing here. Now, if you are differentiating here, it is a independent of AI, it is 0, and if you are differentiating here, you are getting -1, which is there. Similarly, if you are differentiating this equation, then corresponding will your third row, here AR is independent. So, it will be 0, if you are going for AI, we are having this term. So, this A1 AI will go off. So, K1 here we have written VTI cos gamma I, and if you are going to differentiate here, it is independent, you are getting the 0. So, this is the element corresponding to this. Now, if we are going to calculate, the main trick is that we are calculating this A and C, that is it's not 0 here, most of the terms are here 0, and it is very simple one. But let us see first the calculation of D corresponding to those. Here the D calculation you can say here, now we are differentiating with the VTJ. Here the Vt here J, why I am writing, because the Vt is your one will be R, means we are differentiating this. I can write your the D matrix is nothing but it is your 3, sorry, yeah, it is some mistake here, because this will be not this. We can write here, this is your, we are writing this D is your corresponding to your here 0 0 D, and it was your E, it was corresponding to your R1. So, I can say R1 here, it is your Vt into Vt, because the Vt is 2 in our case. So, here if I write this R into here R1 del Vti into your Vti. Then here it will be your del R2, here this is the Vtr into Vtr, here del R2 Vti, and here Vti just it will be multiplied. Similarly, here it will be your Vtr del R3 for del Vtr, and in here R3 del Vti here Vti. So, it will be your 3 cross 2 matrix. Basically, this is not correct, it is basically the compute from the previous one. So, it is not correct. So, this we have to delete here, and we will see what the values we are getting. Now, this R1, if you will see the R1, in R1 whether it is a dependent on, you can just see this equation here, this R1. If R1 you are differentiating with the T, here there is no Vtr. So, this term will be 0, because the R1 you can see here, if you are differentiating with the Vtr, there is no Vtr. So, it is 0. Now, this Vti, it is also 0. Now, the second term here. So, this is 0, this is 0, here K1 AR, here Vtr will be also there, mind it, because we are multiplying here. So, this value we are going to have, it is your K1 AR Vtr cos alpha r. So, this value will be this. Now, this will be with the Vti, it is not there, it will be 0. So, this is again 0, this is 0, this is 0. Now, this it will be 0, because this equation here now with the Vtr it is 0. So, I can say it is equal to 0, but this will have value, and this is your K1 AI Vti cos gamma I. So, this will be the value. What I did, just I wrote, it is easier, no need to remember, just simply write R1, R2, R3, these are the rows corresponding, and the variables here the Vtr and Vti's are there. So, this is your D. So, only the problem here if you are calculating this A and C, because in the A and C here it is not R1, R2, R3, this you see the matrix here, this A is corresponding to your real power of the terminals of the HVDC, derivative of XDC, means I can say A already, even though we have defined also in this one, this is I can write, this is will be your 2 cross 3 matrix, because the P, the TR and the TI are the 2 rows here. So, I can write here del PTR del whatever in this case your X1, and this is your AR, because we are in this case we are having our unknowns AR, AI and your VDR. The 3 are the your XDC in this case. So, this will be this. Now, here your PTR, your AI, and here PTR VDR. Similarly, here we have to write this PTI, your AR, here PTI AI, and here PTI del VDR. Means we require a function of here the PTR that is in terms of AR we have to see. Means we are interested to write the equation of the PDs basically, and this PT is the total power, that is the change in the power if you remember, and this we wrote here, then PT here at that bus the rectifier terminal, it was your the P specified at that bus minus I said the PAC, that is a voltage and angle here, just you remember here, minus I said here PDR, and this PDR is function of your VTR, VTI and XDC, and this is a just I can say general function, maybe it is a variable dependent on 2. Now, if you are differentiating this with your XDC, this will be 0, this will be 0, because they are the independent. This is the AC, here only this is a dependent on XDC, this is a function of XDC and the VTR, VTI. So, if you are differentiating here, means effectively it is a minus here I can say PDR over XDC. Okay. Here the minus term is appearing. So, this we can add here, this minus will not appear. Why? This you remember we can write this equation, here we want it equal to 0. Then you can this minus, this plus and this plus, because the Jacobian element how you are writing this H N and JL here, if you are writing this is a negative elements, then it will be also negative. So, this is if you are, because this will be the same sign here with this sign, means what I can say here, you can write this f x is equal to 0, this is also equal minus f x is equal to 0. So, if you are differentiating the taking the Jacobian here, so you are just doing minus in this way or that way, both are same thing. Means here you can say this is your, this is minus, this is a plus and this is plus here, because anyway we want this 0 this value. And then you are differentiating, you can say this is 0, this is your Jacobian elements. So, in Jacobian what we do, we take it as positive. So, that is why it is in the positive coefficient. So, main care here is that we take this is nothing but it is your element of your H and we normally take it in this way. So, same expression you have to write, otherwise this will be adding and subtracting together. So, you cannot get the converse solution. So, in this case normally we prefer this. Again this depends upon whether sign is plus or minus, this will be decided by how H, N and JL you are defining. So, normally we do take this as a positive elements, Jacobian elements. So, that is why it is additive of this. Okay. So, here we are also taking the positive here. Mind it here, this is for the rectifier. So, the rectifier here, this and this is added together. If you are going for inverter, this will becomes negative, because it is just coming just like a generator. So, only difference in the real power, however the reactive power always it is taken as load and it will be coming out from the bus. So, now means this differentiation is nothing but I can say it is a PDR upon XDC. So, I can replace here it is your DC power of the rectifier end, here the DC power at the rectifier end, and here is the DC power at the rectifier end. Similarly, we can at this here this PDI I can write, but this sign will be negative here. So, okay. Why I wrote negative here? Because the converter it is just coming out, inverter going in, so it is a sign change. So, this minus sign will be coming. Still it is not sufficient. Now, we should know this what is the PDR at that terminal buses. If you remember this, we wrote the first 1, 2, 3 equation, then later we write the equation for the power. Means the power equation what I write here, the PDR it is nothing but your VDR into ID. And you can see this is a function of here one of the control variable. Here I am taking ID as a constant, because our the specified variables are alpha r, gamma I, VDI and PDI here. So, from here you are fixing these variables, means your ID is constant. So, it is independent of VDR now. So, here ID is a constant, or you can write this here is a PDI divided by VDI. I have no problem, because these values are given to you. Now, this PDI is a constant value. The PDI here is the constant, and we are already specified value here. These are the specified variables of the DC. Now, you can see here, from here if you are differentiating, this is 0, this is 0, and here if you are differentiating, means you are going to get your PDI by your VDI, that is ID. This is a constant. So, whatever you are derivating, it will be 0. So, this is your A. So, it is simple, but if you go for C, it is not so simple, because in C now you have to calculate the reactive power. Real power is simple equations we write. Now, we have to write this reactive power, and the reactive power we can write in terms of apparent power. So, apparent power equation also I derived and I wrote the various apparent power, if you remember. I wrote 1, 2, 3 are the basic equation, then I write the 2 more the real power equations, then I wrote a equation for current, and then later I write the SDR, SDIs. So, here I require this SDR, it was, what is this value? K 3 root 2 AR VTR into ID by pi here. Similarly, we wrote for here SDI, it is K 3 under root 2 over pi AI VTI into ID. We have this, we have the P here, PDR and the PDI. Now, we have to calculate the QDR and QDI. So, your QDR we have to write a function. Now, we are getting this function, because this is your one of the variable. This T is a here it is coming in the AC. So, we are is not taking care here, because other elements have already taken care of this, and ID in this case is also constant. So, here you have to write the QDR as here SDR square minus PDR square, and here I have to write the QDI, it is your SDI square minus PDI square. So, this is the constant, and we have to now differentiate this now with the reference to other variables. Means now here I can write this C, here it is nothing but here simply I have to write Q, here 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 simply I have to write the Q. Remaining thing will be same. Moreover, here this sign in this case will be positive, because the Q is taken a load at both inverter as well as the rectifier terminal. So, this element you have to again you have to derive this from here with this equation, and then you have to differentiate it. So, you are going to get some terms here, it is not 0. It's okay. Now, let us come to this our eliminated variable methods or variable elimination method. It's different names are given in the different papers. Now, what here we are doing, that Jacobian we were extending. Now, we saw that's your R1, R2, R3 here it is a function of your VTR, VTI and XDC variables. This is the vector, this R1, R2, R3, three equations are basically nothing but they are the function of your rectifier terminal voltage, that is AC terminal voltage, and inverter AC terminal voltage, and then XDCs are 7 variables. From here, if it is 0, we can simplify XDC in terms of this value. Means just you can write XDC, whatever your 3 now XDC will require for solution here in this case. XDC here for this control mode, here it is your these 3 values. So, we can just simplify and we can get it because the 3 equations are there. We do not want the explicit equations because it is a partial derivative. It is not just you have to have exact value without dependent of any other variables. It can be because we are doing the partial derivative and also we are solving these equations by any iterative solutions. So, it will be automatically taken care. So, that is why here it is written some we are not deriving the explicit equations because these are the nonlinear equations as well, and it is not possible that you can have independent of all these 3. So, here the PDR you can see I can write the PDR which were appearing here is a function of again this value your maybe this dependent on this and your XDC means from these 3 XDC here can be replaced and we can get another function that is having only the VTR and VTIs, means in that we are not interested to have the XDCs, and this is your now if you are having this and this is in your Jacobian form because we require the AC terminal voltage of rectifier and as well as the inverter, and then in whole remaining part it is going to be modified. So, we will see in the normal Jacobian here what is happening because I wrote this equation here. Now, this is also going to be a function of your VTR and VTI. XDC we have eliminated from equation 1 to 3. So, this is also having this AC and then you can differentiate this. So, what happens once you are differentiating here with the reference to your VTI and VTR, for others it will be not changed, but the VTR and VTI this term is going to be added in this Jacobian term because this is also having VTR and VTIs. So, only at the 2 points when the rectifier and inverter this term is going to be added. So, this will be only comes when you are going to differentiate with the VTR and VTI, and you will find here here means your this is your Newton-Raphson equation in the polar form here these corresponding to only voltage because corresponding to delta there is no change because we have not changed only because this PDR is a function of VTI and VTR only no delta. So, here H and M are constant only here the L and the N are now going to be modified due to the DC variables at DC part because the power is going from this rectifier and coming in to your inverter. So, this here elements of this are going to be modified only corresponding to the terminal voltage of R means this rectifier and inverter. So, it will be the 2 here corresponding to P means here the PTR and PTI here corresponding to VTR and VTI means in this the 4 elements here maximum also here the 4 element. So, the maximum that is why here written the 8 variables are to be modified. Why I am talking maximum I am not saying only 8 because it depends upon what is the type of bus. If it is your not a load bus it is a generator bus it will not appear that one VTR and VTI. If your one rectifier terminal is a slack bus that will not come here because this is only the other than slack bus. So, it depending upon which type of this is your where the terminal that is I can say rectifier where you are taking, and this is going to be here your inverter, this is your I. So, what is type of this bus in your AC load flow, whether it is a PV bus, whether it is a PQ bus, whether it is a slack bus. So, if one is slack bus here in this, then corresponding to that there will be no change. So, if it is a slack bus, let us suppose rectifier is slack bus. So, I am sure this will be not a slack bus, but it may be a generator bus. So, if it is a generator bus and another is your slack bus, then only the here we are going to have the 2 terminals, 2 variables of this, and there will be nothing here. This will only arise when we are having the load bus. Are you getting my point? Because so this is a very you must be very careful that what is the type of bus at there. If this is slack bus, because in your P here this slack is not included. So, this and also in Q slack is not there. So, this bus there is no change, R will be not there. Only in I now we have to see what is this. the possibility is I can say here, if R is your slack and your this I can be your PV bus and can be your PQ bus, right. So, if this is slack bus R, so neither it will be having here nor it will be having here. So, the 2 rows are gone. 2 rows means again the 2 here, the voltages also we are not concerned. So, 4 gone. So, only now if here is a PQ, then we will have 4 elements. If we are having the PQ type this bus, then we are going to have 2 elements only. Okay. If we are having both here PQ, means if we are having a good chart here PQ and PQ, then we are going to have 8 completely. If you are having this is one is your PV, then and another is your PQ, then why here? So, I can say here 8, here how much? It is going to be 6, because 4 corresponding to this, 2 corresponding to this. It is easy to calculate now. Now, if we are having PV, then 4, that we came here. No. So, all possibility here I can write if we are having the PV, then we are having 4. If we are having what else possible?
Reverse is also same.
Here the PQ and because is the reverse is same. Now, another here is a slack. Here if you are having PV, then your 2, no. Here we have written, yeah, PV, then it is 2. And if it is here PQ slack, then we are having 4. So, these are the elements, only these elements are modified, and it is very easy to modify. So, that is why this elimination variable method is very variably used. Means we always try to use, because only the limited number of elements just you have to change in that one iteration, and again you have to go for that. Well, now let us see this how the elements are going to be modified corresponding to the your R and means rectifier and inverter end. Now, let us see this L. As I said, only we are going to modify the corresponding to your R, that is the rectifier and the inverter. So, the corresponding to your P, we are going to write here this I can say LPP. Why I am writing the P? I am writing this terminal TR is as a P. Otherwise, we can write TR, because what is the name of this bus? This is your, if it is a terminal R, here this is your terminal I can say it is Q, here it is P. It is easy to just denote. So, I can say LPP here, which is going to be modified. It will be corresponding to this with that variable here, means it was in the original. When we are not adding this, so this is known as your LPP. Now, whether it is a plus or minus depending upon what is this value, here we are going to write this plus. If it is a rectifier, now I am writing the TR is P here. So, it is a rectifier, and so and rectifier that is taken as a load. So, this value here, now we can write this here VTR, or I can write the VP here P into your PDR, here this element is to be added. So, that is why here it is written the VP, VDR, and this function whatever now we are having only the simplified this equation having the VTR and VTIs. So, this PDR is you just only the difference with the previous PDR here. Now, this is only function of your VTR and the VTI. I can say it is a function of VP and VQ. I am writing here the VTI is as a Q. So, at the rectifier here, these are the only values are going to change. Now, then here LPQ, it is your prime LPQ. Now, here we are going for the inverter. This will be again the positive, because the same equations we are deriving. because this LP here, the TR we are writing the expression, means your element here in this complete L, I can say it is your LPP, here somewhere LPQ, and here I am writing this LQP and somewhere LQQ. So, these are the various elements, various rows. It again in whole your it is n by n, this order of the complete L is your the variable the V, and this is your n minus 2 number of buses, corresponding to this your value is number of PQ buses, because the bolt is where we are going to determine. So, in this here the 4 elements are going to be modified. So, this is I am writing here this P is again the TR. Now, it is a differentiated with the its VTR, and here we are differentiating with the VTI. So, this is your plus here VQ, I can say del PDR here VQ, and again this is a function of VP and VQ. So, this is your, that is why here it is written, this is the plus if you will see, and then we are having this differentiation of Q. Q I am assuming that is the inverter terminal here. Now, we can also get this QP. Now, we are just writing the power equations for inverter and differentiating here with the reference to the T terminal voltage. So, this is your LQP. Now, here it is we are writing the power inverter, then power sign is a change than your Jacobian sign here, as I said, because here the Jacobian sign here whatever you are element having, it is going to be added at the rectifier terminal, at the inverter terminal the DC variable is just treated as a generator. So, it will be negative here, and then it will be your VP here PDI here VP, and your LQQ prime here LQQ minus VQ del PDI over here del VQ. So, these are the 4 elements corresponding to your Q. It is going to be changed. Similarly, we can also get for your M, and you can write, no need to write here. We can just simply write here, instead of here this we are writing N. Now, here the P will be changed by Q, right. Here it will be the plus for all the case, because the Q is taken as a load. So, here instead of negative here that becomes positive as well for the Q. So, here in this case if you are writing N PP prime, then it will be here no doubt this is N PP plus here the VP into del QDR differentiated with your del P. Here it will be again same here NPQ prime will be NPQ plus here the VQ into del PDR differentiated with your del VQR here. If you are writing NQP prime will be your NQP plus here will be there, and this here only changes your Q. Here also this is N here plus, and here going to change QDI. Only the problem what happens to write the equations here the PDR and PQR is simpler in the DC system, but once you are going for the reactive power you can see the equation going to be complex. It's a slightly you have to modify, because you are going calculating the SDR from the PDR, you are going to calculate the QDRs and QDIs. So, that is you have to do, and you will find some elements are appearing. Now, for this case also, if we can just calculate this example, that is a control mode A. In this case also we can just try to calculate. So, let us see how we can get the different elements corresponding to their control mode A. If you remember, same we solve for your extended variable method as well. So, where your variables alpha r, gamma I, VDI and PDI are given to you, means we require so 3 variables, and that here again I can write this is your AR, AI and it is your VDR. So, these 3 are your XDCs basically, but since it is a extended elimination variable method, we do not want this. It is not coming at all, because already we are just simplifying R1, R2 and R3 equations in terms of VTI and VTR. To simplify this, here no doubt this you can see this ID is here constant, because the PDI and VDI are there. So, it is we derive this equation. Now, this power at the rectifier end, here what we are having, we require the following variables, this PDR, we require this PDI for these, and then we require your QDR and QDIs. So, these 4 variables we require at all. Already the PDR we know, it is in terms of PDI, we can write here it is your PDI plus the losses ID square your RD. Okay. Means here if you remember earlier what I wrote this VDR into IDRD, no VDI into your ID. Means what I wrote, this VDR into ID is the PDR, means here this VDR into ID. I do not want the VDR XDC, as I said, we want to eliminate it. XDR, what is your X here? VDR we do not want at all, because it is a elimination variable methods. So, these 3 variables should not appear at all, because the 4 variables, other 4 variables, they are specified, that will be there, you cannot eliminate at all. So, here we do not want the VDR, and this VDR we know that we can write, this is another equation. So, here if we are just multiplying here, means we are getting the PDI and IDR and all the things are known in this case. Now, the PDI here, it is your PDI only, it is a constant. So, now I can just remove this, and that is why here I have written this PDR here, this is the PDI plus the loss of the line, the DC line. Now, to calculate this SDR, because we require SDR before going for this, means here I can say your SDR square minus your PDR square, and similarly here we have to also write your SDI square minus PDI square, as I said. Okay. Now, from here if you will see the SDR, this equation we wrote, in this case we do not have any here, this variable we are having, so we have to eliminate this. We do not want this, we want this VTR, we want this alpha, because alpha is specified, and other ID we know, so we do not want this. So, how to do this? We here in the SDR, because here in the PDR you can see there is nothing here, those variables. In SDR we can see we have it. So, what we are going to do from here, this value alpha r, we can just VDR no doubt is a one of the variable, but the VDR we know it is a function of VDI plus RD. So, that is there, so that we can eliminate again. So, from here what I did, this AR VTR we are taking, and thus we are replacing here. So, we will get a function, how I can write. So, let us derive this value. So, from here I can say it is your AR VTR will be equal to this VDR, it will be going that side.
Pi by 3 XZ.
Yeah. So, it is your VDR plus 3 XC by pi ID 1 over. Here we can take this coefficient even though this, because already it is lying here. We have this term also, this term we can take it here. So, 3 under root 3 AR VTR we can write, 3 under root 2 we can write. So, this pi is also there, yeah, pi we can also take here, true, pi we can take here. So, this is your this value divided by cos alpha r. Is there any problem?
Second pi is not there. VDR plus the pi we have taken from.
Acha, the pi we have taken, right, sorry. Pi we have taken, yes. Because we are taking, no, it should be there, man. It will be this pi, because what we are doing, this pi is coming here. And this pi is already there divided, this divided by both. So this will be there, this pi we are taking here as here.
So, is it VDR or IDR?
This is VDR.
Yeah.
It seems like
No, it is this VDR, right. Now here VDR also will replace. Before that, now I can put this value here. So your SDR I can write this value here directly, means it is nothing but k times of this, because SDR you can say k times of this value is there. So I can write here k divided by your cos alpha r. Here your VDR also I want to replace, it is your VDI into RDID. One equation we wrote here in terms of VDR. Whatever VDI is there, then the drop in the resistance, that will be your VDR. Here plus 3XC over pi into ID into here ID. This ID is also there, so we can multiply here ID. So what we are getting in this case, it is nothing but your k with your cos alpha r. Here it is a VDI into ID, it is your PDI. This value is your loss, I can write it is your PL. RDI square here, this is also here ID square and X here, this is again the loss in terms of your reactances. So here I can say it is a QL. So we are getting this function SDR in this sense. Now you can see this value is also constant. This is independent of your VTI and VTR. This is already independent of your VTR and VTI. So if you are differentiating this with respect to your VTR and VTI, it will be 0. This is independent of this VTR VTI, the differentiation of this will be 0, here this will be also 0, here also it will be 0. Now let us see here. Similarly, you can see SDI, what changes we are doing, instead of this, this is AI will be there, means I can write this is for that, it is your I, here VTI, here it is your, and instead of this I have to write gamma I, and if you put the value here I, it will be I here, it will be here your gamma I. Okay. Now this is the VDI is already there, so this term will not appear, means here this is not there, and you can see this is also independent of your VTR and VTI. It means, and if you are differentiating with this VTR and VTI, because this is a constant, this is a constant, that is independent constant I mean, and then you are also getting 0. So your all 8 elements, whether 8, whether 2, whether 6, whether 4, it will be 0. So very simple. The control mode A means it is a simple your Newton-Raphson Jacobian. Means here what we are getting, whatever here was, this is your L and your n prime, it is nothing but it is your the same value which was your there. What I wrote here, I wrote M, L, J, H, Hn, yeah. So here H here, H and here M now. So to avoid this confusion, even though earlier people were using this, that's why we go for J1, J2 and J3, J4. So it is very simple. So here you will find there is no change in the Jacobian at all in control mode A, and it is good. But if your here AR is hitting the limit, then what will happen? We have to fix this and alpha R will be going into the picture. means your control modes where you are just fixing. If it is heating, then it will be changed if it is a rectifier side. So, your control mode B here you will find it is here where AR is fixed now, because AR is hitting this, not is alpha, is AR is hitting limit. So, AR is now fixed to its limiting value, gamma I, VDI and VDI, PDIs are there, now they are specified. And now we have to calculate, then remaining the variables are here, that should be calculated. What are the remaining variables that we need now? Here it is going to be simply alpha R. So, we have to eliminate alpha R, AI and VDR from those equations. So, it is again the similar procedure, similarly we have to follow. You can see SDR we have again writing here. Here the alpha R is now fixed, it is known to you. So, this is the constant. Now, leave this. Here the PDR will be as it is, no change. Your PDI is also there is no change. So, you can see the PDR and the QDR again here, this PDR and PDI are is a fix, this is a fix, differentiation with this it will be 0. So, that is why here you can see this is related to LPP element, the modified element which we are adding, means here we are L plus some element we were adding, then it was modified. So, we are talking about here this additional element which is going to be modified here. So, this element which is written there, how much we are going to add or subtract. So, this value is 0 for the corresponding to the P, means it is all here corresponding to here the 2P, here the 4 elements are 0, and you can see here the all the 4 elements are 0. This PDR, PDI, PDI here VTR is 0, here also 0. Now, only we have to see here, one is your SDR, another is here. In this AR VTR, AR is fixed, VTR is fixed, PDR is fixed, then it should be also 0.
No, VTR is not fixed.
VTR not fixed, but we want it the function of the VTR, because it can be a function of VTR and that we require. So, this is not constant. Here this term AR is fixed, but this is a function of VTR which we need it. If we will go here, this will be the constant again, because in the similar fashion what we derived for this one, this is not going to change here this value. So, this is the constant, this is a constant. So, this will be constant, the derivative of this means 2 elements are gone. Now, only we have to see, because this is a dependent on VTR.
Is VTI constant?
VTI is not constant, it is not dependent on that. In this equation you will not find the VTI anywhere. But now, this equation earlier the far we were writing, we were eliminating, this is a, if you remember here AR and VTR together we were eliminating, and then we were finding it was a constant. Now, here this AR is constant, VTR is a function, you cannot eliminate now. So, this is a value here we are getting in this term. So, what happen if you are differentiating this? So, in general you have to differentiate, means you are just you are writing here differentiation of this your QDR. We will also find it is a VTI is 0, because this SDR is function of only VTR. The VTI is 0, so corresponding to that will be also 0, and that is why it is written here. The Q here 0, this corresponding to VTI is it is 0, means we are getting here this QDI and the QDI with the both here this is 0. One side here VTI we are just making 0, only one element is going to appear in all the 8 elements. And again, whether this will be there or not, it depends upon the type of this R bus as well. If it is a PB bus, PQ bus or slack bus, then it you have to see whether it is required. If it is a PB bus, it is not required. If it is a slack bus, it is not required. If it is a PQ bus, then the Q is going to be there in the Newton-Raphson Jacobian. And then if you are modifying here, differentiating this, you are going to get this SDR here square upon QDR. means simply you can differentiate this with respect to your here VTR, here VTR, what you are going to get. Here I can say 1 over 2, this is 1 upon QDR, whole this term, because this is power 1 by 2. So, is a minus, so it is coming down. So, QDR I am writing here, then into the differentiation of this term differentiation is 0, this term we are going to get, means it is your 2 into SDR, here differentiation of SDR by your VTR. And since we are going to here multiply VTR, here I have to write the VTR as well. Okay. The VTR I have multiplied here. I wrote for the differentiation of this 1 upon 2 QDR into, now we are differentiating the inside term. This will be 0 constant. So, it is the twice of SDR into the differentiation of the SDR with respect to the VTR. Now, you can see the SDR here. It is directly we have the function here SDR is the VTR. So, this will go off, but we are multiplying VTR again, the first term. So, here you are differentiating and you are multiplying here, you are getting again this term is going to be your SDR, means it is your square, this 2 is cancelled and you are going to get your SDR square over QDR. So, in whole you are in this mode, you are going to have this one as well. So, now you can say here, even though you will see, even though you can generalize also, if your the variables are here your alpha r and your gamma I, whatever here the two variables we are specifying, all will be 0. If you are fixing these two, remaining here whether whatever VDR and whatever writing, you will find that it will be the all 8 elements will be 0. If it is changed, then correspondingly you have to change it. So, this is one another control mode B. If it is a given another control mode, here basically control mode A, B, C, D, which I am writing here, I wrote in the last lecture, it is again it is a depend upon the different what you are talking. It is not a very standard, this is a control mode A means this is the specified control B means specified. So, for you even though it is given what are the specified variable, what are the unknown variables, then you have to derive or you have to calculate the various elements of the Jacobians, etc. So, this is your nothing but your Newton, this is the extended variable methods, and here we discuss the Newton raption in terms of polar form. It is not possible to have it in rectangular form because it becomes very, very complex. Here it is not our meaning to make it complexity, and you find it is very, very simple. Sometimes there is no need to modify it here, or maximum we have to, maximum we are going to modify only the 8 elements. Then we also find even though inside, even though let us say 8 depending on the control modes, there is a possibility there is no need to modify. So, very few elements are going to be modified. Now, the question you can say, if this Jacobian is not modified, how HVDC is going to be taken care? If there is no change, means it is only AC load flow, means where is the DC now? Basically that DC term is appearing in terms of mismatch, because here every time we are multiplying here inverting this to calculate those variables, here no doubt we have your del P and del Q. So, in del P and del Q that DC links variables are coming into the picture. So, it is there whether you are modifying here or not, and then correspondingly we are calculating here our this change in the delta, change in the V by V, and we are solving this equation. It's clear?
So, ultimately alpha r and gamma are there, then only you will get one element.
Yeah, it is alpha r and gamma I is there.
The variables, if they came into the variables.
No, there is a possibility you can you can get even the 8 variables. If here you are changing something here you are changing, whatever you are having here, you are going to get this. So, there is a possibility that is only the 2 cases you are getting the all 4 0, because various combination of these 7 where the 4 are going to be fixed.
So we are going to calculate, because basically load flow is going to be a snapshot type. So we have a specific alpha, it is operating, specific gamma, it is operating. For that condition only we are able to.
Look, what we are normally do here in this case now, what is the check? Here, even though we are not checking any variable of the DC variables here, which is going to violate, which is not going to violate. Once you are calculating this, you are just calculating this value of VTR and VTI, and based on the VTR and VTI, you have the DC variables you can calculate it. And once it is hitting here, then you can again modify it. Because otherwise what will happen, there may be you cannot get the solution converse, because if here you are not checking, suppose alpha is coming something 180 degree, yeah, your A is coming 200 in that calculation, that means there is not a solution. So once you are just converse here, you have to check these variables whether they are in the specific limit or not, because anyway you are checking the Q limits also of the generators. Similarly, you have to check what is the limits of this HVDC variable at that. Yeah. And then again you have to, then your control mode will be keep on changing. So here the ones you have specified, but once it is hitting, then your control, like your PQ and PV buses are changing every iteration. Here also these values are going to be, modes are going to keep on changing. So you are keep on changing, modifying these elements. So you have to check which are the going to hit, fix it, remaining you have to make it and keep on doing it. So this is your HVDC AC/DC load flow. Thank you.